All right, welcome back. Our next presenter is Paul Edwards from Microsoft.
Hi, so I'm Paul Edwards and I'm part of the Azure HPC engineering team. I've been working at Microsoft for 5 years and I help customers run and migrate their workloads, HPC workloads on Azure. Today I'm going to start by giving you an overview of the Azure HPC stack and share some of our successes. Then I'm going to take a deeper dive into the HPC infrastructure and show some benchmarks. And finally, I'm going to do a demo of Azure HPC OnDemand platform, or AZHOP. This is an open source accelerator project, and it brings together all the building blocks on Azure to create a similar experience to Azure to HPC on-prem. So first, the Azure HPC stack. So the HPC offering spans compute, storage, and networking capabilities. And these are all the components that can be used to deliver the performance and the elastic scalability to meet your simulation and modeling needs. So we have the transformative services for your AI and ML workloads. The workload orchestration components provide the on-demand and elastic scalability. These components include provisioning the raw infrastructure with virtual machine scale sets. We do cloud-native scheduling with Azure Batch. We've got the more traditional HPC experience with schedulers such as LSF, Slurm, PBS, and that's with Azure Cycle Cloud. And then we have the Azure Kubernetes service. One of the clear differentiators with Azure and HPC is our networking. And on our optimized compute, then we provide an InfiniBand network. And so this provides the low latency for your tightly coupled jobs. The optimized compute consists of H-series, which is our traditional HPC nodes, and the N-series for your compute and visualization GPU nodes. So overall, it just gives you a scope of what Azure as a platform and service can do for you. So on Azure, then we've demonstrated applications running tens of thousands of cores, and we ran the Graph 500 BFS benchmark, and this entered the rankings in November 2020 at number 17. Here we used 40,000 cores and reached 1,151 gigatraversed edges per second, and we're still currently at number 25. We're not actually aware of any other public cloud doing the Graph 500 runs. At the launch for our HPV2 compute offering, then we ran Star CCM Plus, and this was with the largest model, publicly shareable model, which is a 1 billion Le Mans car, and this was run up to 57,000 cores. Now the scaling was really good, and we obtained 99% parallel efficiency at 44,000 cores and 84% at 57,000 cores. Another benchmark we ran at the launch of the HPV2 was a weather research and forecasting model. Here we ran the WRF model for Hurricane Maria on 80,000 cores, and we actually got 110% scaling efficiency at 15,000 cores, and it was reduced to 72 at all 80,000 cores, but this was due to the limited model size. And this was actually a case that we could compare against UCAR published data on attack system, which was number 20 in the top 500 in 2016. And on Azure, we ran 672 dual-socket AMD Rome nodes and got 2.2 times the performance of the 1,024 dual-socket Broadwell nodes. We work with the Beckman Institute at the University of Illinois and scaled NAMD to 86,000 cores on the 210 million atom tobacco mosaic virus. This was 40% higher scaling than the team had ever previously published, and it achieved 76% parallel efficiency. So the slide's slightly out of date here. So the highest number of cores on competing clouds currently stands at 40,000 cores, still 2 times lower. But most of these results I'm telling you now are on our older generation HPV2, which are the AMD Rome nodes. Now we've got the HPV3, which is the Milan X nodes, and we've introduced systems with thousands of A100 GPUs. And in fact, with one of those systems, then we actually entered the top 500 at number 10, getting the impact performance 30 petaflops last year in November. So another recent success is with the UK Met Office and Microsoft partnership, where we're building a weather and climate forecasting supercomputer here in the UK. It's a 10-year contract, and the first 5 years we're going to be delivering 6 times the performance of their current systems. To do this, we're going to be hosting 4 HPE Cray supercomputers, and we're going to integrate those to Azure. The next generation, so the second 5 years, then we're expecting to go native cloud-based supercomputing. So it's an exciting project, and in addition to the pure compute, we're going to implement a massive archive data system growing to 3.7 exabytes. And we'll take advantage of the other Azure HPC capabilities, such as the interactive HPC and virtual desktop services. Other news that was made public back in May is our partnership with Meta, where Azure was selected as the strategic cloud partner. So as part of this deeper relationship, Meta will expand its use of Azure supercomputing power to accelerate its AI research and development for its Meta AI group. So Meta are using 5,400 GPUs, the latest NDM GPU series, for their large-scale AI research workloads. And these are the NVIDIA A100 Tensor Core 80 gigabyte GPUs. This was another showcase of our differentiation with the InfiniBand network, and this low latency is, we were getting 2 times the performance of the other cloud providers. Okay, so let's take a deeper dive into what the infrastructure available in Azure. So here's an overview of the different types of VMs we offer on Azure, and it really shows how the cloud provides a complete range of VM sizes. It's no longer the case where a single choice is made for all workloads. For example, not all HPC requires low latency networks, and high throughput workloads could benefit from general purpose VM types. And here you can take advantage of spot pricing as well if your workload supports it. However, today then I'll focus more on the specialized VMs, as the workloads acquiring these VMs typically have been the most challenging. Or most challenging to run in the cloud anyway. So this is the current lineup of the H series. So our most recent is the HP V3, which is on the AMD Milan X. We're offering 120 cores per VM, 448 gigabytes of memory. There's 2 960 gigabyte local NVMEs, and the 200 gigabit HDR network. So we can see from this table the performance is increasing through each generation, and so that's one thing that we do. We continually improve and get new products out. And one statistic that's actually not shown on here is in the table is the level 3 cache. So in fact, the HP V3 has 1.5 gigabytes of level 3 cache, which is 3 times the size of the HP V2. This is particularly good for some CFD workloads. So this slide really shows the evolution of the HPC VMs offered and shows the constant HPC improvement on Azure. So one thing to point out here, because we have the 2 HP V3s. The HP V3 was originally on the Milan, was originally delivered on the Milan, but we subsequently updated it all to Milan X. And so we've got charts here showing the relative performance for a Fluent 140 million cell race car across the different VMs, and so they're being compared to the oldest one, the Skylake here. So the chart on the right is it's a nice example why we need to size jobs properly, because it's the same Fluent case run multiple times with different numbers of VMs. And as the number of VMs increased, then to 64 VMs, running on 64 VMs, it's actually 127 times faster than a single VM. And this better than linear scaling is because as we scaled to more VMs, then more of the dataset was actually fitting in the level 3 cache, which is why we saw this performance. These are some more benchmarks here with comparisons between the different HPC VMs with Fluent and OpenFOAM. And we're actually highlighting here the improvements that we actually got going from the Milan to Milan X. So the HPV3 with Milan X was up to 80% higher for the CFD workloads, 60% higher for EDA, and 50% for FEA. So this slide, it provides more details on the WRF run that I mentioned earlier. It shows the scaling running from the WRF simulation of Hurricane Maria, and we were able to run up to 80,000 cores. To deliver the 1 kilometer resolution, it used 371 million grid points. And we can see where the scaling stops at 512 nodes, VMs, but it's actually the WRF model resolution. If we could have scaled the model bigger, we could have continued scaling there. So I'll move on to the N-series VMs that we offer, and we have 3 different classes. We have the NV for visualization. The NC is the more traditional HPC compute, so the reservoir modeling, DNA sequencing, Monte Carlo simulations, and of course it can be used for inferencing or deep learning, but it's the ND which has been specifically designed for the AI and deep learning workloads. So this is the complete list of the different types that we have. The most recent compute and deep learning VMs now have the A100 GPUs, and the main difference with the ND is that we have the InfiniBand networking, and with the ND we also have 8 GPUs per VM, and we don't split that up, whereas with the NC then we have you can either have 1, 2 or 4 GPUs per VM. So we ran some NVIDIA deep learning examples and then MLPerf benchmarks that consist of real-world compute-intensive AI workloads. And from this, we were able to achieve the results on the NC A100 V4 that is competitive with on-prem performance for both single and multi-GPU systems. We also compared the results with the latest NC to the previous generation, to the NC-V4 to the NC-V3, and the results always showed at least a 2 times improvement in performance per dollar, and some benchmarks actually reached up to 4 times improvement. Okay, so now I'm going to show you a project that the HPC Specialized Compute Group that I'm in has built as an open source community project to build best practices for deploying an end-to-end HPC environment on Azure. And it's called Azure HPC OnDemand Platform, or AZ-HOP. So it aims to provide the on-prem HPC experience. We combine the Azure components with the open source software to achieve this. And for our group, then it really provides the platform to demonstrate different building blocks that can be included in an HPC setup. And all the features that we have been the result of customer engagements. One of the key components is the Open OnDemand web portal. Open OnDemand developed by the Ohio Supercomputing Center, and it's actually NSF funded until the end of next year. and it's highly used in a lot of the US supercomputing centres. So what we build on top of this is we do all the provisioning in the back end, because Open OnDemand is typically being used as a portal for on-prem clusters. And so before I go into the different components, I'm just going to quickly run through a typical on-prem HPC workflow. And this was the first sort of use case that we had when we were creating AZ Hub. So quite simply, I mean, end users, they typically access a cluster through a login node, for example, with SSH. They'll submit jobs to a scheduler, and then the jobs will be scheduled and run on the compute. There'll be some form of shared storage where the results will be written, and then users will wait for their jobs to complete, and then might then use a visualization node to view the output. And then the whole system has a user directory for authentication. And so that workflow was the original starting point for the project, but we've since extended that with more building blocks. I'll go through what we have. So we have OnDemand as the portal. The deployment, we use a YAML config file, and then the current version uses Terraform, but we're actually moving towards Bicep, which is the more native way to deploy on Azure. And the benefit there will be it will simplify deployment, and we can also start to think about making it something we can put in an Azure marketplace. The setup and configuration is through Ansible, and for images, then we've actually put the compute and the visualization VM images into the Azure marketplace, but we do include the package scripts in our repository. And you can actually create a shared image gallery on Azure, so that you can, if you want to modify and create your own images, then we can do that. We have the storage with Azure NetApp files, and then we actually the Azure NetApp files is for the home directories, and then we have Lustre as the parallel file system for the data. And to provide the archiving for the Lustre file system, we deploy the Robinhood policy engine in combination with the Lustre hierarchical storage management and our own Lustre metadata synchronization tool. So this automatically archives all the data, including the metadata, into blob storage. We deploy Active Directory for identity, and then we can use AAD if we want to do two-factor authentication. We do monitoring with Telegraph, Influx, and Grafana. And so we've set up some dashboards there. And so at the moment, then we're currently supporting OpenPBS and the Slurm schedulers, and then CycleCloud does the scheduling, does the orchestration and auto-scaling. And we've actually integrated the CycleCloud UI into Open OnDemand, so you can actually see what's going on in Azure in the back end. So another thing we've added is one of the engagements we had needed health checks, because sometimes you get your nodes, if they don't work, then if the InfiniBand device doesn't come up or something, you need to do some sort of health checks to make sure everything's working correctly, otherwise your job queue can empty very quickly. And so we've integrated the LBNL node health checks, and this is run before nodes actually get added to the be scheduled on. And then finally, we've got visualization. So we do Linux visualization with NoVNC and VirtualGL, and we've got Windows virtualization with Apache Guacamole.
So we have one question from the audience. They were asking, is Lustre Metasync publicly available?
Yes, it is. It's I'll paste the URL in after. It's okay. Yes. Now the fun bit. So I'm just going to switch. It worked. So this is Azure. Once you've installed it, then you'll have your web page. I'm running over a VPN, and so this is what the portal will look like on the main page. You'll be able to. Yeah, I mean, it'll show you your login, you've got access to everything from here. So going back to that original use case, then I mean, we have from this portal, then we can browse our files. And so and you can actually upload or download files to this, so you can get your data onto the system or take data off. Wherever you browse to, it does actually have a file viewer as well. So I can view a file or edit a file. It's not one that I would typically use all the time, but I mean, if you want to quickly edit something, it's there. At any point, then you can drop into a terminal to where you are, and you can access the terminal from the main page anyway. So now I'm running PBS on this one. I can look at my job queue, and I can actually submit something. So I've just submitted a job, OpenFOAM running. You don't have to use the terminal for things. Open OnDemand does actually have, you can view your job queue from the portal. And so we can see that I've just submitted this job. And we can see at the moment the comment can't ever run insufficient amount of CPUs. That's because we don't have any at the moment. CycleCloud should be doing its job, and it should be, at the moment, provisioning something for us. And so we can check that. So this is a product, the Microsoft, one of Microsoft's products, and we're just embedding the UI behind Open OnDemand. And there we go. I submitted a job for two extra nodes, and it's now acquiring them. And so you can see what's going on here. So as you start putting things into the queue. Okay, so now let me just go to the monitoring. Then I can just quickly show you the Grafana dashboard. We have one for all the different infrastructure that AZ Hop creates. So whether the scheduler, Cycle, Robinhood, Grafana, etc. Or the other one, we have one for Lustre. So here we can see how much data is on the system, how much is released, how much is still live, because Robinhood will maintain, if you go over 80% full, then it will start archiving stuff and releasing it from the file system. And so the other thing, so if I go into, we have the interactive apps, so I can, this is where we can launch our Linux desktops, or we have Linux desktop, Windows desktop, or the other one that we have is a code server. So it's basically VS Code embedded in the web browser. It's sometimes quite a nice way if you want to edit files and have terminals all together. It's quite a nice way to work. So code server would look like this. So I've got my terminal, and I can edit my files, and it's basically VS Code. But if I go to my Linux desktop, then we have the desktop, so you can have your desktop session that you can keep running. We're running virtual GL, so I can, if I just run a benchmark first of all, we can see it's the frames per second, 600. It's picked up the M60 Tesla card. And I have PowerView running for the case that I'd submitted from a previous one. And so, I mean, you can use your 3D applications. Okay, I'll switch back.
with it?
Lost my window, sorry. Okay, so I've just given a brief demo of AZ Hop. If you're interested to find out more, then I've got all the links to our documentation. I should actually add the HSM to this. And we'll also be running a workshop at Supercomputing. If anyone wants to join, there's a link there for it. And so, yeah, I hope, well, what I've shared today, then I hope it inspires you to try out Azure Cloud. And if you've got any questions, please ask.